and PhD degree from Malviya National Institute of Technology, Jaipur, from our department, and he has numerous publications in the application of the optimization algorithm in the field of seismological signal processing, or you can say the earthquake signal analysis. And we will be listening from him about the application of these techniques on this niche area of research. So with this, I welcome you, Dr. Ashish, to this particular
Thank you, sir. Thanks for this
forum.
opportunity. Thank you.
So you can share your slides.
Sure, sir. Is my slides visible, sir?
Yes, yes. Please make it full screen.
Is it fine, sir?
Yeah. Yes. That stops sharing. You can do it. Yeah. Okay. Minimize that one. Yeah. Yeah.
Okay. So, good evening, everyone. I'm very delighted to present.
Your video is.
This.
Can
Okay.
you
Okay.
make the camera on?
Yes.
Yes.
Okay.
Now, can you please share it?
Sure, sir. Is it visible now, sir?
Yes. Yes. Yes.
Okay. So, good evening, everyone. I'm very delighted to present here the overview of this chimp optimization algorithm and with application to seismic signal processing. So there is two part. One is an algorithm, another is its application. I know you already have discussed about many algorithms before, but it's maybe new for you. Some important parameters, some important updates are there in this algorithm. Not only we will discuss about the single objective optimization, but later we will also see how to develop the multi-objective version of this and how we can apply this algorithm, especially in the field of seismic signal processing, or we can say seismicity declustering. These are the outlines of my presentation. So first we will discuss about the chimp optimization algorithm, its history, what is the main idea behind that, how we developed this, what is the social life of these chimps, what is the inspiration from those social life behavior of the chimps, and its implementation part, that what are the parameters over there, what kind of population over there, what is their division, how we can use those as an exploration and exploitation of the phase. Later, we will see its structure and we will apply its multi-objective version and many objective version in a seismicity declustering. So chimp optimization algorithm was developed in year 2020 by the scientist known as Mohammad Khishe. It is a nature inspired algorithm. So whatever algorithm is nature inspired, it is inspired by some of the species, like particle swarm optimization is there, which is inspired by the movement of the particles. Gray wolf optimizer is there. So this was developed with the social behavior of chimp optimization or chimps. So it is another population based algorithm. So why this is population based algorithm? Because any algorithm can be inspired by some species. That species live in a group or maybe alone. Okay, for example, the Aquila optimization algorithm, it is only single bird is there. Based on that single bird, algorithm was developed. But in case of chimps, these chimps live with the family, with a group of 10 or more than 10 individuals. Those individuals are males, females, kids, all other persons are there. So it is another population based algorithm in which more than 10, which is size is more than 10. And it is inspired by the hunting behavior of the chimps. So how they hunt a prey and what strategy they use. This was inspired the researcher Mohammad Khishe to develop this algorithm. Later, our team developed the multi-objective and many objective part of this. I will show you how we developed. Okay, so the chimp operation simulates the chimp's life their behavior and especially the hunting process. Now we will go little brief detail about the chimps. What are the chimps are, how we bifurcate them in different groups, what is the responsibility of each group, and how they perform their behavior, and how this all inspired us to develop this algorithm. So chimps belong to the F family and are recognized as one of the most intelligent animals. Why most intelligent animals? Because the DNA of chimps are similar to the humans, and scientists has reported it is 96% of DNA of humans, and these chimps are similar. So that's why these are considered as a very intelligent one, and due to their high brain to body ratio. They live in a groups where each group explore its environment. Environment basically means search space. For example, if they are living at particular place, they look the surroundings. What things are available over there, where we can get the prey, where we can get the water. Okay, so where each group explores the environment search space using different strategies. Now, this is very important part. Different strategies. Generally, in most of the algorithm, all the particles follow the same strategy. But in this case, they follow different strategies. And that's why this algorithm is very efficient to solving many applications or many different kind of multi or many objective applications. In a chimp group, each individual has different methods of hunting. I will come to this particular line that why different hunting methods are there. So now there is a big colony. Suppose 15 size of chimp is there. Maybe few are males, few are females, few are kids. So the responsibility of hunting or exploring or searching for the prey for a food is given to the four important individuals, which leads the group for the hunting process, and those four individuals are known as drivers, barriers, chasers, and attackers. So we consider them as that these are the strongest persons in the family. They have responsibility to go out, look for the prey, hunt them, and feed the entire family. So these four are drivers, barriers, chasers, and attackers. Now, if these four are doing this, what about others? Other persons are there. They also have some responsibility. Now, first we will discuss about the responsibility of these four drivers, barriers, chasers, and attackers. Then we will look at the responsibility of others who are normal chimps. So drivers are the responsible for pursuing the prey without catching it. Okay, so as a driver chimps looks or found any prey, he start following it. Okay, but he do not catch them. He just follow them. Okay, now it started following. Prey will move from his position. It will go some other position. Now there is another chimp, which chimp is known as barrier. And barrier constructs the obstacle. Barrier do not allow chimp to escape from the given path. So it is already, strategy is already decided. The trap is already decided by these drivers, barriers, attackers, and the chaser, that we have to allow the prey to follow a certain position or to certain path. And they are making this strategy doing this. Barriers constructs obstacle to avoid the progression of the prey. Chaser. The role of the chaser is to swiftly follow the prey to close the distance and keep up with its movement. So chaser start following it. And finally, the attacker. Attacker predict where the prey will try to escape the route and make it turn back toward the chaser. So these are the four important responsibility of driver, barrier, attacker, and chaser. Now, for the next slide, you will able to understand. So this picture was we made this picture and from the paper, that is a many objective chimp optimization algorithm to decluster earthquake catalogs, which was published in soft computing in 2024. Now from this picture it is clear this black app is our prey and this is a driver. So driver as looks at the prey suddenly changes its position and jumps to another tree. When it jumps to another tree, there is another chimp is there, which is known as barrier chimp. Barrier chimp stops its path and barrier start following him. Now what happens? Again, prey changes its position. It reaches to other location where he found the chaser is there. And at one position where attacker is already there. So all these three chips, driver, barrier, chaser, allow the prey to follow a certain path. That's why we call this as a trap. And when the prey reaches to the certain position, all these together attack on a prey and they get their food. So this is a very intelligent strategy they follow. And each individual, each chimp over there has certain responsibility to perform. But there is some other things also there. Okay, so I hope this is clear to everyone. Now the social life and explanation. So four chimps have some responsibility. Now these four chimps may be one, maybe two. Okay, two may be attacker, two may be barrier. Any number of chimps may be barrier, attacker. It doesn't matter. Now what about the rest of the ones? The rest of the chimps in a group follow the four leaders. Now these four chimps are moving ahead. Then rest of the chimps calculate the position of these four chimps and update their own position. Okay, so we can say that they update their position based on the leader's movement. So the rest of the chimps in a group follow the four leaders, adjusting their own position based on the leader's movement to help in hunting the prey. Now, what happens in a final stage? This is very quite interesting. That's why in this algorithm, the chaotic uh, coefficient was also added. Now, what is a chaotic coefficient? You will see in many research papers, there's a chaotic optimization algorithm. So this chaotic part is also here. So in a final stage, all chimps hunt simultaneously. Now, as prey is dead or prey is found, four chimps start is responsibility to take the or to divide the food. But other chimps who are following these leaders, they cast aside their roles, maybe because of any social favor like alliance, mating, grooming, or any other motivation. They cast aside their role and try to catch the prey or try to get the food chaotically in the final stage of hunting process. So all together, all the, I'm not saying all, maybe few, but more than these four chimps participate in a hunting process and try to take this food as much as they can because of these alliance, mating, and grooming or social favors. So this is one of the interesting things. So overall, what we have seen what is the social life of the chimps, how they look for the prey, how they attack the prey, and how we have divided these chimps in different categories like drivers, barrier, chasers, and attacker. Now, how to implement all these things as a mathematical formulation? We will look into this and how we develop this, how the authors develop this algorithm. Now, before starting, let me just clear to you. Okay, so whenever you develop, you have to decide that what is the size of your colony. It may be 10, 15, 20, whatever. Okay, so size of the chimp colony is constant. In the chimp community, we discussed earlier that there are four kinds of chimps: driver, barrier, chaser, and attacker. And the hunting process of chimp is comprised of two major parts. Now, every algorithm which is nature inspired, which is inspired by any species, particle swarm, grey wolf, chimp, or whale optimization, all these algorithms has two very important part, was this exploration and exploitation. Now, what is the meaning of exploration? Exploration is basically to explore globally. Globally, basically outside the boundary, which is the best solution available. And exploitation basically means that to look for the local solution. And it is very important to make the balance between exploration and exploitation. What will happen? There is no balance between exploration and exploitation. Your solution will not converge. Diversity will be less. And this is very important in case of multi-objective optimization. The diversity and convergence should be high. Solution should not uh, stop at one position only. They should be diversified. Then only we can say that we got the best result. Okay, because in case of multi-object optimization, there is multiple results are there. So it is important. Now, if we talk about exploration and exploitation in terms of chimp optimization, so in exploration part, exploration phase of hunting comprises of driving, blocking, and chasing. So there is a three chimps are there: driver, barrier, and chaser, which perform the duty of driving, blocking, and chasing the prey. Driver chimps has a responsibility to follow, avoiding any fight. Barrier chimps obstacle there, and chaser chimp chase the path of the prey. And in case of exploitation, all chimps hunt simultaneously to obtain food as much as possible to deal with the social favors like alliance mating, what we discussed earlier. So these two things are important, and we will see in the next slide. Now, as I told you that there should be exploration, and exploration must be have like the balance should be balance between exploration and exploration should be there. How to make the balance, or how to the exploration should be good. Okay, for that purpose, we should always initialize our population randomly. If you will not initialize your population means number of chimps, number of size, what is the size of your number of chimps is there. Okay, so it is very important to initialize. That's why if you read any paper, you will see that every initialization is done randomly, and randomly between the upper bound and lower bound. We cannot go to up to infinity. We have to decide certain range, and that range is decided by the upper bound and lower bound. Similarly, here in this case, the chimp position is d-dimensional. Suppose we are using d-dimension and upper boundary is b high and lower boundary is b low, then you can initialize the population, n number of population between these upper bound and lower bound using this formula, where I will go from 1 to n and j will go to 1 to d. D represent dimension, n represent number. N will be 10, 20, 100,000, whatever you decide. Okay, so random initialization is very important for any optimization algorithm to avoid bias. If bias is there, your algorithm will not converge. Next, I told you that in a social behavior, they follow the prey, they drive it, they chase it, barrier. All these things are mathematically implemented. Now, we are doing optimization. The aim of optimization is to find the best solution. If we talk in layman term, so for a chimp, the best solution is prey. Correct. So if chimp has to find the best solution, he should reach at the location of prey. Now prey is continuously changing its location. Chimp has to change its location also. Now how to change the location? If we know the distance between the current location of the prey and we know the location of chimp, then chimp can understand, okay, my distance is this much. Now every step I have to move towards prey. So the distance calculation is one very important thing. So here in equation 2, x prey represent the location of the prey and x chimp represent the location of chimp. Any chimp. I'm not talking about attacker barrier right now. Any chimp. Now, if the distance is calculated, in next iteration, we will start decreasing this distance. When we will start decreasing this distance, we will move towards our prey. So this third equation, what we are doing? Now, initially, the x chimp was the position. In a next iteration, t plus 1, t is starting from 0, 0, 1, 2, 3. In next iteration, it will change from its first location towards next location. Okay, so second and third equation is moving chimp towards prey. Okay, now it is moving, but there is some parameters over there. These parameters are coefficients, which are p vector, ch is chaotic vector, s represent the coefficient vector, x prey, x chimps are position. These parameters are very important. Now, what these parameters are, I will let you know. Now, in case of exploration, these parameter p and s are calculated as s equals to 2m vector r1 vector minus m vector divide, and p vector is 2r2, where r1 and r2 are the our random values between 0 and 1, and the value of s is decreasing between 2.5 to 0 iteratively. Now this particular value was given in the fundamental paper. You can choose another value also, but 2.5 is sufficient value for this particular value of m. Okay, so 2.5 to 0, it will start decreasing. Now what is the role of this s? It is very important role. Now here you can see at every iteration we have to move towards prey, but here also we can see that this r is a random number. Now random number can be anything, okay, between 0 to 1. Sometime it will increase, sometime it will decrease. So what will happen? Because of the random initialization, this value will change. Okay, now we can see this in the next slide. We will see. I will come to this also. So S has responsibility to move the chimp towards prey. S vector has responsibility, and other M, and M is 2.5 to 0, decreasing, R is random values. Now I told you earlier that every chimp, there is 4 chimps are there which are playing in the role of attacker, driver, barrier, and chaser, and they all 4 uses different strategies. What basically mean different strategies? If you all follow the same path, suppose straight line you are following, or circular line you are following, or spiral line you are following, okay, so all chimp have the same kind of exploration. But in case of chimp optimization, what authors did, author made a certain mathematical formulation for each chimp. For attacker, they decided this function, which is 2.5 minus 2 log t divided by log t. For a driver, they decided another function. For barrier, another function, and chaser, another function. Okay, and all these 4 functions depends upon only 2 things. One is total number of iteration, that is log t, and small t, each iteration 0, 1, 2, 3. For example, t equals to 100, capital T equals to 100. Then t will start from 0 till 99. So the position of each chimp, here attacker is green, red is barrier, brown, blue is driver, and this is chaser. So over the iteration, their value is reducing from 2.5 to 0. And this dynamic coefficient M is given by this mathematical formula. Now, here we can get a very small idea about our research. What idea we can get? We can change these functions. You can change any other random function, and you can check whether our value is increased or not, or our complexity is reduced, or our timing is reduced or not. Okay, this may be the small part of research if you work on this particular kind of thing. Okay, any optimization algorithm. Okay, so this is the role of this dynamic coefficient vector, which we discussed here, M. Okay, now this is the graphical representation. Now on paper, we can represent only 2-dimensional and 3-dimensional plane. So that's why I use these 2 figures only. Multi-dimension is not possible. Now you can see here, suppose in case of 2-dimensional, our prey, which is this prey, is present at the center. And all these red location belongs to the location of chimps. Chimp can be here, chimp can be here, chimp can be here, anywhere. Suppose chimp is here. Now what S will do? Here this is S. What S will do? Based on the value of S, our chimp will move towards prey or away from the prey. And it is always expected that chimp should move toward our prey. Then only we will able to reach at the final location or our optimal value or the prey location. Similarly, here is another 3-dimensional representation in which we can see that our chimp is here, and the prey is located at the center. Now this chimp can move in any direction. How to decide that we have to move towards only our prey or our food? Those things are decided by these values S. This S value, M value, R value, they decide that it will move always towards prey. Now with every iteration, our prey may move. Okay, so our prey may move, then only these 3 factors will keep changing the value based on the random value R1 and R2, and our chimp will move toward the prey's location. Okay, so this was the exploration part. Now what is about exploitation? Okay, so now we have 4 chimps. So far we studied about how to update the position, how to calculate the distance generally. Now it is applicable for all chimps. So 4 type of chimps are there. The attacker will look at the, so attacker is there. Attacker will calculate its distance. Barrier will calculate its distance. Chaser will calculate its distance. Driver will calculate this distance based on their position. And any random chimp present in the group will look at these distances only. D attacker, D barrier, D chaser, D driver, where they are located right now. Based on their location, other persons or other chimps which are not part of the attacking process will update their positions. So in the end, suppose x1 is the distance between any random attacker. So attacker x1 is the distance between the x1 and attacker. X2 is the distance between barrier, X3 is for chaser, X4 is for driver, then any random chimp will update their position using this particular formula, which is given in question 8, X1 vector plus X2 vector plus X3 vector plus X4 vector divided by 4. Let me make you more clear with this picture. Look at this picture. So we know there is a location of chimp. So chimp is there. Okay. 4 kind of chimps are there. One is barrier, another is attacker, third is driver, fourth is chaser. And any other random chimp which is not part of the attacking process, but it is following because it is a part of the group. Correct? Now this chimp, which is over here in a brown, it will calculate its distance from attacker, from chaser, from barrier, from driver. So all these distances calculated here. Okay, so all these distances will be calculated by him. So these distances will be calculated. Okay, based on these distances, now as they will move, it will update its position. So what is the position of these? Attacker, driver, barrier, distance is calculated. Based on distance, we will calculate the position. So how to calculate the position? X1, X2, X3, X4 are the position of attacker, barrier, chaser, and driver. Now what will happen? Based on this position, any random chimp which is x will update its position. So xt plus 1 equals to x1 plus x2 plus x3 plus x4 divided by 4, and this is the position update for all those who are not part of attacking process so far, but they will update their position based on these 4 leader chimps. So this is the exploitation attack. And now we also discussed that chimp also perform the very interesting kind of thing in which they forget their responsibility and they attack chaotically. So what we consider here, what authors consider basically, that suppose 50% of the population do not participate in this chaotic process, but rest of the population participate in chaotic process. So we use this factor eta in this. If eta value is greater than 0.5, then chaotic attack will be there. If eta is less than 0.5, the normal position update will be there. And this chaotic attack is designed by these 4 different mathematical functions, which is Singer, Bernoulli, Tent, logistic, quadratic, and Gauss. Again, these are mathematical function, but this is kind of position update using chaotic process. Position update using chaotic process. So either you update position given by the normal process, or you update your position based on these chaotic maps, and this mathematical equations used to simulate the behavior of chimps in at the time of final stage, where they, because of some social incentive, they forget their responsibility, they cast aside their responsibility and attack on the prey. So this is the all the process of the chimp optimization algorithm. Now, these suppose we have to develop any multi-objective operation algorithm. There is 2 very important things. First is archive controller. Second is leader selection. If you want to convert, suppose in your studies you have studied any single objective optimization and you want to convert in a multi-objective case, in this case, then you have to develop this multi-objective version. But for multi-objective version, you have to integrate 2 important parameters with a single objective algorithm, and those 2 important parameters are archive controller and selection mechanism. There is one more thing is there, which is crowding distance. Either you can use crowding distance or you can use archive controller, and leader selection is there. So what is archive controller? In a case of multi-objective operation, I think you all know now what is multi-objective operation. There is a concept of Pareto optimality or Pareto dominance, in which case there is only there is a number of solutions are there, but which solution we have to choose. So with every iteration, we will select one solution and we will save that solution in archive. Okay, in next iteration, again one solution will come, and should we have to select in the archive or not, it will be it will depend on the dominance factor. Okay, if the new solution is dominated by the archive, it will be not be added in the archive. Initially the archive is empty. Okay, if new solution dominates at least one archive member, then it will be added, and the previous one will be removed. If both archive member are new member, does not dominate each other, then both will be added And in case of if your grid is full and new solution is better, then you will apply some grid mechanism there, in which you delete the one existing solution and you add new solution into the archive, and archive contains all the possible solutions there, okay, which is the best solution we can consider. So this is the process I'm talking about. So first one is the grid mechanism, so in which we store all the possible best solution, and all these are the best solution, and every time the new solution will be inserted at particular location if it is free. If our grid is full, or we can say our archive is full and new solution is better, then what we will do, we will delete one of the solution which is poor or which is bad solution. Okay, after that we will decide which is our best. Now we got a lot of solution, which one is our best solution, or which is our leader attacker, which one is our attacker. That attacker is decided based on its location. The least crowded solution is considered as the best solution. For example, if we have to choose attacker among this the below figure, then this red one is the best solution because there is a least crowded. How to select this red solution mathematically? So the roulette wheel selection technique is used, which is basically tells us that it is the less likelihood solution. You can select this as the best solution, and this red one will be our the best solution. So single objective algorithm is there. If you want to convert it to a multi-objective algorithm, you have to integrate either archive or crowding distance with roulette wheel selection technique to select the leader. So this is the process. Now I have discussed about chimp optimization, multi-objective, how to develop the multi-objective version of Swift. Now we will look how we can apply these algorithms in seismic signal processing. Now the application of optimization in seismic signal processing. Now, especially we will discuss about the seismicity declustering. First, I will give you the brief idea what is declustering, and then we will come to the our topic. So seismicity consists of two types. So you just consider that seismicity is our earthquake. So there is two kind of earthquakes. One is regular earthquake, which is known as background events, and another is aftershocks and foreshocks. Now, what is aftershock, foreshock? What is background events? I just tell you. Right now we are not feeling any kind of earthquake, okay, everything is stable, everything is fine, but still there is a movement going on inside the earth crust. Those movement is because of the tectonic plates. These tectonic plates keep rolling from one place to another place, okay. Because of this, there is always some kind of vibrations are always there, which is recorded by our recording stations, and those are very important for geologists. So background are basically when there is no earthquake, still you will feel some kind of triggers, which is recorded by the our background, which is recorded by our recording station known as the background events. But in at the time of earthquake, there is large magnitude or large intensity earthquakes are there just before the main shock. Main shock is basically the earthquake which has highest intensity. So before the main earthquake, you will feel some aftershock or foreshocks, and those all aftershock and foreshocks are related to each other, and they happen due to many reasons. They may be because of the dynamic stress change, seismically activated fluid flow after sleep. Okay, there is many reasons behind these seismicity activity. I'm not going in those seismic part. Now these figures will be clear you what is the aftershock and foreshocks. So these yellow curves, this bar chart will show you these yellow curves or yellow bar lines will are basically the background seismicity. Okay, and at the same time, suppose at some time any main shock comes. So this is a main shock. Main shock basically means the earthquake with magnitude of 8 or 9. We can consider it as a main shock. Okay, so if any main shock comes, before that some earthquake comes. After that even some earthquake comes, and they all earthquakes are related to these main shocks. So those events which appears before the main shock are known as foreshocks. Those events appears after the main shocks are known as aftershocks, and they are all are related. Now, what is our objective of seismicity declustering? Our objective is to bifurcate these two categories of event. We have to isolate the events, and So we can say that background should be removed from the clustered seismicity, and clustered seismicity must contain only main shock, foreshock, aftershock. And in seismology field, it is widely used. It is widely used in a probabilistic seismic hazard analysis. It is widely used in a modeling of process. It is widely used to estimate the rate of the main shocks and the forecasting when the next earthquake can come. For the probabilistic hazard analysis tells us that if earthquake comes, what kind of possible damage will be there, and when what is the estimate rate of the main shock. One earthquake will come, three earthquake will come, thousands of earthquake will come at a particular location at certain time. So those all estimates are only possible if we have a clean data of background and earthquake events. That's why it is very important to bifurcate these two categories of event. Now, I just told you what I told you, that we have to classify the earthquake events in two categories. So we can say that it is kind of classification problem. But we have not labeled data set. We don't know this which data belongs to the main shock, aftershock, and which data belongs to the background activity. Correct? Okay, so that's why we use the clustering algorithms to solve these things. And we can also develop these optimization algorithms, and which can help us to design this. Now, first we will discuss about what is earthquake data. Then I will also so as I told you, we are classifying the data our earthquake in two categories. One is background seismicity, and another is our aftershock activity or main shock activity. Okay, so two categories are there. So we also modified the chimp optimization algorithm in a binary form. Now we'll see how we can develop the binary version of the chimp optimization algorithm. And if you want to develop any algorithm or the binary version of it, you can also use the similar kind of thing. Okay, so earthquake catalog. Earthquake catalog has very important characteristics. Four major parameters are there: latitude, longitude, which tells us which is the location of the earthquake; time, at what time this earthquake appeared; and the magnitude, what was the intensity of the magnitude. You can see here in the right figure, this was the seismicity map of Japan for last 30 years, from 1919 to 2024. And you can see all these red dot represent the major earthquake activity, and yellow dot represent the little less than the major main shock, and blue events represent the different earthquake activities. Right now we cannot say which is background event, which is background event, or which is the aftershock and main shock. This is just a map. And here from these arrows, it is shown that 2011, this Tohoku earthquake was one of the deadliest earthquake ever appeared in history of entire world. This was Tohoku earthquake, which is large casualty was there. Then Hokkaido earthquake, Hokkaido earthquake, 2024 Noto earthquake. All these red dots represent the earthquake. Okay, so this is an earthquake catalog. As I told you, we have to bifurcate this in two categories only. So we can say this is a binary classification. Okay, so what we did actually, we considered that one, we don't know any earthquake belongs to which category right now, but we considered it randomly, that this earthquake is considered as aftershock, this considered as a background, this considered as aftershock, this considered as a background. Now we represented our earthquake in this form. That's why we assigned value 1 and 0 to every earthquake event, and we are considering it as a this is aftershock, it is a background event. What will happen as our algorithm will run, these 1 0 values will start changing, and these 1 0 will start changing at the time of the last iteration. We will get certain metrics in which tells us that this data belongs to the clustered seismicity and this data belongs to the background seismicity, or this is known as the binary classification. Okay, and what is binary classification? To develop any binary classification, we need a one mathematical function. Okay, and that mathematical function is there is a lot of sigmoid function is there, exponential function is there. Okay, you can use any kind of mathematical function for your application. It depends on you only. Okay, on which mathematical function you are getting better results. Okay, we developed this binary multi-objective chimp optimization algorithm using the sigmoid transfer function. Sigmoid transfer function, I have not I think the diagram is not included into the function, but this is given by 1 upon 1 plus e to the power minus x. So this mathematical equation represent the sigmoid transfer function. Okay, So in case of binary, the result should be 1 and 0. Okay. Now our in our algorithm, step size is there, position update is there. So position is changing from one place to another place. Chain position is changing, correct? And it can take any continuous value, 0 0.1, 1.3, 2.5, 10, 2.3. We should strict our algorithm to reach at 1 and 0 only. And it can be done only when you use certain kind of mathematical application which restricts our algorithm to give the output as a 1 and 0. So that's why we use this sigmoid function. Now I'm not going this detail why it's very easy. There's no much thing is there. And then so x attacker b step value is greater than 1, then the final value will be 1. We mapped it to 1, and it is less, then it will be 0. In this way, we mapped x1, x2, x3, and x4 in 1 and 0. Okay, and finally the value is between the random value is less than 1/4, then it will belong to the x1 or attacker. If it is 1/4 to 1/2, it will be the x2, 1/2 to 3/4, it will be x3, and 3/2 for 1 x4. So these x1, x2, x3, x4 we divided based on this random value because we have 4 attacker, driver, barrier, and chaser. If in your algorithm no 4 attackers are there, only one is there, then you use directly one value. But here, because of this, and again we use the randomness just to increase the diversity and the convergence of the given algorithm. Now, if you want to apply any optimization algorithm in any field, first you have to understand what is the objective function. Objective basically function means to optimize the value. Just I was listing the before. Cost is there, comfort is there. If you want reduced cost, comfort will not be there. If you want high comfort, then cost will be high. Correct now. Okay. Similarly, these are the objective functions. In case of seismicity, we use two very important objective function. One is coefficients of variance and Morse-theta index. Now, I just told you before that earthquake has four different categories. Four different type of important parameters. First is latitude, longitude, which is space. Another is time. Third one is a depth, and fourth is a magnitude. Okay, so here we use the two important parameter. First is coefficient of variance, which represent the time information of the earthquake data. Second is the Morse-theta index, which represent the space information of the data. And these two parameters are contradictory. If they are not contradictory, you will not able to apply or you will not able to solve this your optimization algorithm. Okay, now these are the like definition of the coefficient of variance, which is the basically the mean statistical parameter. This is, and it is basically the standard deviation normalized to mean for the inter-event time. Now, one event happened, another event happened, another event happened. So the time difference between two consecutive event is if delta t, then ensemble of delta t square, ensemble of delta t whole square root divided delta t is known as coefficient of variance. Now just forget about this definition, what it represents. If the coefficient of variance value is equals to 1, then the earthquake event distributed uniformly distributed, or we can say if C, because we are calculating or we are dividing in two categories. One is background category and one is a main shock or aftershock category. So if the coefficient of variance value equals to 1, it is uniform distribution, or that particular event represent the background seismicity. If the coefficient of variance value is greater than 1, then it is distributed according to power law distribution, which represent that it is the clustered seismicity. So what we are doing it basically, we are optimizing it, and after optimizing with a binary multi-objective chain optimization, we are getting some value for the each particular event. Based on that event, it will be classified as either background or as our clustered seismicity. And second parameter which we used is Morse-theta index. Now this is another seismic parameters. Right now maybe you will not able to understand what this is, but I'm just explaining you. Okay, so suppose this is a box, and in this box there is this black dot represent the earthquake event. Okay, whatever data, it doesn't matter, earthquake data, seismic data, whatever data, these black dot represent the earthquake event. Okay, and this S line is our diagonal. This S is our diagonal line, correct? Now what we'll do, we will divide this box into smaller regions with the power of 2 to the power n. Okay, now it is entire one box. and this left graph, black, this dotted line is there, one red dot is there, this represent the value of Morishita index. Okay, right now the value of Morishita index using this formula is this dot over here, left top one. Now we divide it in a 4 different groups. So obviously data will remain same, but group is divided. So one group is there, one group is there, one group is there, one group is there. Now what we'll do, we will calculate the density in every particular quadrant. Okay, based on that density, what will happen as we reduced our diagonal, or we reduced it in a number of quadrants, this will be increased. This Morishita index value will be increased. Why it is increased? Now we will calculate the Morishita index value for this quadrant. This quadrant had 0 because no data is there. Then again we will calculate for this, we will calculate for this, we will calculate for this, and the highest value we will choose. So this will be the value. So in the left axis, in the y-axis, it is I value. Reducing the size of a quadrant, our Morishita index value is increasing. So here it is increased. Again we divided, obviously it will be increased. Again it is increasing. Again we divided, it is increasing. So these are the two parameters. Now, if it is increasing, it is clustered seismicity. If it is increasing, it is represent our clustered seismicity. If it is 0, then it is dispersed solution. Okay, and if it equals to 1, then it is a Poisson process or background seismicity. So these are the two important parameters we used. And how we can get this data, earthquake catalog, there's a website which is United States Geological Survey website. You can search on internet, you will find this, where all seismic data with all these parameters are given and freely available to download. So if you feed these parameter setting over there, you will get some location where you can download your data set. Okay, and when you will plot this data set, this will be the spatial distribution of all the data sets. So here black dot represent the entire data set. So far we have not clustered it or declustered it. Okay, we have not classified so far. So Himalaya, California, Indonesia, and Himalaya, Japan is there, and California is there. So this is the spatial distribution of these earthquake catalog. And when we applied our chimp optimization, binary multi-objective chimp optimization on these catalog, we got these Pareto funds. As this problem is the minimizing problem, we choose the value which is closest to the origin. So if we consider this is the closest to origin, we choose this value is the closest to origin, we choose this value, and based on this value, we will get the value of coefficient of variance and Morishita index with each iteration. And then we classified our earthquake catalog in 2 categories, in which we found that all these events, colored events, are clustered events, which are belongs to some different clusters. Okay, because as we know, we took the data from 1990 to till 2024. So some activity head into 1990, some activity head in 2024. Okay, so based on that time thing, these all earthquake data set is divided, and these all color data set is clustered data set. What about background data sets? And these are for Indonesia and Himalaya. This was for Japan and California. So this is a representative clustered seismicity, and these results belongs to the background seismicity. So all are uniformly distributed. Okay, so this is just a visual part. Okay, this is just a visual part. Visually we can see. So we divided in 2 part, and after that we just plotted on these maps. But how to justify that this is a background and these are clustered seismicity? So there is some tools are there, or we can say some parameters are there. Those parameters are known as, first is cumulative plot. So cumulative plot tells us about that our data is perfectly segregated or not. Now I told you that background seismicity is uniform seismicity. Okay, so if any data which is uniformly distributed, if you plot its cumulative plot, it will be always straight line. So here blue is straight line in 4 categories. So what we did, this black curve is our total data sets. Okay, this black is our total data sets. And when we applied our algorithm, it was classified in 2 categories, which is pink and blue. Now, if it is correctly classified, our blue curve will be straight line. And in all the 4 catalogs, our blue curve is extremely straight. We can say that our algorithm correctly classified. So this is a representation. And now, and one more thing, what is significance of this up is like in 20th year, so if 1990 is 0, then and 30-year data set is there, so we can say 1990 2020 till 2020 data set is there. So in year 15th year or 20th year, there was some earthquake was there, major earthquake. So all of a sudden number of events increased, all of a sudden within a short span of time. So that's why we can say that there was some major earthquake activity appeared at that particular location. So here we can say at 20th year, or it may be 1990, 2010 or 2011, some activity happened, and that's why there is a slight increase in earthquake activity. Same thing appeared here in a pink curve, which is an aftershock curve. Okay, because background seismicity is random, it is uniform. Okay, it should not have any changes. So here our uh, aftershock activity follows the similar trend as given by the total events, which is also tells us that our algorithm perfectly bifurcated these two events, and it is appeared same for all four earthquake catalog, which is Japan, California, then for Indonesia, and for Himalaya regions. Another plot which tells us that the data is correctly classified is known as lambda plot, and I'm discussing these in terms of seismicity only. For seismology field, these plots are widely used. Again, you can say that blue line represent almost straight line, which represent the background seismicity. But again, our obtained aftershock, which is represented by the pink line, follows the similar trend as given by the total events. So similar trend is followed. So we can say that activities are correctly classified. Here again, you can see peaks. These peaks represent the high seismicity activity. Here, suppose it is 23 or 22.5, then at year 22.5 and the same duration, almost 4,000 number of earthquake events appeared. Okay, for example, here at 21st location for a second plot, at 21st year, around 1,500 earthquake events appeared. So this is the another significance of these plots. And another plot which we can be used to bifurcate that our earthquake event is correctly classified or not is the two parameters are there, which is inter-event time and inter-event distance. These inter-event time and inter-event distance are basically the time difference between the events and the distance among them. And if you plot those on a log scale, if you plot those against each other on a log scale, you will find that these blue curves are clustered at the some point and the black curve is clustered at other point, or randomly distributed. So this black represent what happens actually if the seismicity is clustered, your inter-event time and inter-event distance value will be low. So that's why all these black represent your clustered seismicity. This blue represent your declustered event, and also the distance and time of these blue events are higher compared to these black events. This is another justification that the proposed algorithm clearly classified this earthquake events in two categories. And our group, actually, I am the student of Dr. Nanda sir. He taught me everything, and we have published many publications. We are still working on these seismicity applications. And these are the few journal publications which I am showing here. We use the optimization chip optimization published in Applied Soft Computing. Then we also used other algorithm like many objective. Aquila optimization we used for a single optimization. Binary NSJ2 we used, and Rahul, our friend, also used the quantum gray wolf optimization for declustering purpose only. So if you also want to work in this field, then you can refer this paper, you can cite this paper, you can go through this paper, and you found any difficulty understanding anything, you can also contact us through email. So these are the things from my side. Hello.
Yes, Ashish.
Yes, sir. I hope I'm not so much fast, not slow.
No. It's perfectly fine. And participants, you can put up your questions in the chat box.
Any question from anyone? So I think the participants are not, no participant is working in this field of seismology. That's why they are not asking any questions.
No. They
And
will ask.
or so many teachers have already taught them like what is single objective, multi-objective, many objectives. Session is going great from last 7 days I have seen. So the knowledge is good to everyone. Still, if you need any help from me, you can send me email. And regarding seismology, you can talk to me. Regarding these optimization techniques, you can talk to me. I'm from electronics and communication background, and but still, if you want any help from my side, I can help you. So I'm just seeing. Okay, so interesting findings shows a give common application. You can use anywhere. If you search for the chimp optimization, you will see it is widely applied in every field, even in electronics, even in antennas, even in computer science, cyber security. You know what happens actually? These algorithm you can integrate with any application. If you have to find the optimal solution for your any particular application, then you can fit any algorithm. But you should not blindly trust any algorithm. All algorithms are not perfectly well for every application. You have to try different algorithms. Like earlier, ma'am was also said that the no free lunch theorem is there. Because of that only single algorithm, these algorithms are coming in market. Okay, because of, and that's why you cannot blindly trust. One teacher from I attended a talk. He said that you cannot use sword to kill the fly. Okay, so you cannot blindly trust any algorithm. You have to try, you have to test, and you can apply it to your field. And which is very important to know, which is your objective. What is your objective? If you don't know your objective function correctly, then whatever algorithm you will apply, you will not get good results. So you should clear about the objective function, and you should about that which algorithm will be most suitable for my particular application. Then you can fit your optimization algorithm, and you can get the good results. So brute force is there, like hit and trial is there. You cannot say that this algorithm is best. If we can say this gray wolf is best or some PSO is best, then everyone will use the same algorithm. You have to compare. Another thing is that whenever you have to find the best algorithm, you cannot go for 100 or 500 algorithms at a time. You just go for the recent one, apply those algorithm or the benchmark data sets. The benchmark data sets, every year the IEEE CEC introduces the new benchmark data sets. Apply those algorithms on those benchmark data sets, try to find which is the best. Then only you can apply for the algorithm. You cannot say that this algorithm is best. Even no one can say this algorithm is best. Okay, you have to find it. But you just try and test on the different set of parameters, different testing functions, DTLZ, or whatever recently introduced in IEEE CEC. Okay, this is the only single criteria. Yes, so this is the metric. Performance metrics are there. When you apply to the detail any functions, then there is a performance metrics are there, like IGD is there, delta measure is there, error function is there. You will check for all these. We will go through literature. You will able to see. So these all from my side. I will share these PPTs to sir. He will upload and he will share it with you. Thank you so much.
So, thank you, Dr. Ashish.
Thank you so much. Thank you. Good to see you, sir.
Okay, thank you.